Today, I want to introduce you to Graphical-LASSO. Of course, before now, um, I walk you through probabilistic graphical model, or a way to actually represent high-dimensional data in a compact way. And of course, I actually walk you through one of the types of probabilistic graphical model that we call Bayesian network. And I walk you through examples on Bayesian network. Remember, we talk about application in real life, application in medical diagnosis, application in weather forecasting, supply chain, and so on, like that. But why do we find ourselves in this topic, today's topic that we call graphical lasso? Because let me tell you this, we don't just do what we do. There's a reason why we do what we do. Why do we need to consider graphical lasso? I want you to pay attention to the two words here, the graphical and the lasso. When you take a look at graphical, it means we want to make use of network. We still want to make use of a graphical structure. The graphical structure that connects variables together. I may want to talk about maybe brain network connectivity. I want to talk about maybe the combination of returns in a portfolio. I may want to talk about medical variables that are connected. But let me tell you this. Uh, when relationship exists among the variables, it's either some have a direct relationship or some variables have indirect relationship. Of course, I remember the other time when we're talking about probabilistic graphical model, I was able to show you, direct relationship and indirect relationship. But let me tell you this, you know, if I have a lot of variables and I derive either covariance matrix or correlation matrix, situations where off diagonal, please pay attention, off diagonal, maybe either off diagonal of a correlation matrix or off diagonal of a covariance matrix. If all the entries in the off diagonal are non-zeros, I'm going to say that again. If all the entries in the covariance matrix, if all the entries in the half diagonal of the covariance matrix or correlation matrix, if all of that are not zero, then that would be complicated. Complicated in the sense that, you are not able to separate indirect relationship from direct relationship. The situation where all the variable connect is complicated, and when it is complicated, of course, it's actually going to resolve into an interpretation issue. Okay, I'm going to say that again. Situation where, of course, if you want to know how how they co-occur or how they vary together, of course, you need a covariance matrix, right? If you are using a covariance matrix or you are using a correlation matrix in the off diagonal, if all elements in the off diagonal is non-zero, then what that means, okay, you are trying to say all variables connect. When all variables connect with one another, that network is complicated. And what do we need to do? We need to sparse the network. Sparse the network. To sparse the network is, can we have a way to introduce a penalty, okay, a form of a lasso that will shrink, some weaker relationship to zero? I'm going to say that again. Of course, in the network, I'm expecting some variables to have a weaker relationship. When I say weaker relationship, maybe the relationship is not far from zero. If the relationship is not far from zero, when I incorporate sparsity parameter in form of a lasso, that will shrink, those values, associated with a weaker relationship to zero. And the moment we're able to do that, the model is no longer going to be, the network is no longer going to be dense. It's actually going to be sparse. When a network is sparse, of course, interpretation is going to be easy. And that is the reason why we need a graphical lasso. That's why we need a lasso in a graphical structure. Okay. And that is why this particular topic is called graphical lasso. Of course, in the outline, I'm actually going to introduce you to that. Challenge in high-dimensional regime and Gaussian graphical model with lasso. Okay, now I need you to pay attention. Of course, we normally have challenge in a high-dimensional data. What do we mean by high-dimensional data? Let me tell you this. Apart from the fact that, all the variables we connect, okay, that will lead us into a complicated situation where the numbers of features is more than the number of observation, then it may be difficult for you to even compute the covariance matrix. I'm going to say that again. Now, let me tell you this. What do you think I need from the covariance matrix? If this guy here, please pay attention. If this guy, if this guy is a covariance matrix, okay, I'm trying to say X follow multivariate normal distribution. X here mean X1, X2, X3 up to XP. I got so many features. It could be returns from different investments. It could be gene expression. Okay, it could be different kind of stuff. Now, if it follow normal distribution, we're actually going to have the covariance. This is the covariance. But what do we want to achieve from the covariance? We want to find the inverse of a covariance. The inverse of a covariance is what we call precision matrix. What do we use precision matrix to do? We use precision matrix to actually, measure the dependency of two variables. The dependency, with the dependence or relationship between any two variables. Okay, but you know what I'm trying to talk about? Situation, we are in high dimensional data where the numbers of features is more than the number of observation. We may not be able to get the inverse of the covariance. It means the inverse, because you know why we're not able to get the inverse? Because the determinant will not exist. The determinant will be zero. Determinant of the covariance matrix, when it is equal to zero, then it means the inverse is, we are not able to get the inverse. Because to get the inverse of a matrix, I need the adjunct of that matrix divided by the determinant. And when the determinant equal to zero, such matrix is not invertible. And if the covariance matrix is not invertible, then it means we may not be able to explain the conditional relationship among variables. And let me tell you this, we're not able to do that because of the fact that all variables connect. And that is why, and that is the extreme version of the connectivity. Okay, that's an extreme version of the connectivity. Now, situation where all variables connect, okay, the inverse of the covariance may not exist. Okay, and what led to that is because we're working with high dimensional data. We are the let me say this. If the number of observation is more than the numbers of features, we can still estimate the precision matrix, except that there's going to be high density. of connectivity. High density of connectivity means of diagonal of the covariance matrix, of diagonal values entries will be non-zeros. And non-zeros actually means all variables will connect. And when they connect, there's going to be interpretation issue. But let me tell you the extreme, or let me tell you the severity of the problem. The severity of that is when the number of features is more than the number of observation, you may not be able to to get the inverse of the covariance matrix. And if you're not able to get the inverse, then you are not able to get a precision matrix, because the inverse of a covariance matrix represents the precision matrix. Then what do we need to do? We need to incorporate lasso into the architecture. And what do you think the lasso is going to do? Like I said, the lasso will make sure that the weaker relationship, the variables, the connectivity with the weaker relationship will be shrunk to zero. And in that situation, the dense situation will now become a sparse. And the moment you have a sparsity, of course, the interpretation is not going to be an issue anymore. Take a look at this. This is what I'm talking about. If you take a look at this guy here, okay, all the variables here connect, okay, but it is not all of them that connect now, because we've been able to apply a graphical, the lasso. Now take a look at the variable x1 and x4. Please pay attention. Do you see a connection between x1 and x4? No connection. And if there's no connection, you know what we're going to say? There's no connection because initially the relationship between S1 and S4 is a very weak one, and introduction of a lasso, okay, has shrunk that weaker relationship to zero. And because of that, you know what we're going to say? We're going to say X1 and S4 are conditionally independent, given we have observed the rest of the observation. And that is exactly what I'm trying to say here. Please pay attention. Look at this statement here. Can you see that statement there? The statement is trying to say X1 and S4 are conditionally independent. I told you the other time, conditional independent means absence of a directed edge. No arrow between them. But we're trying to say they are conditionally independent, given that we have observed the rest, which means X1 and S4 are not giving any statistical information about each other, provided we have observed the rest. And that's exactly what I'm talking about. Okay, now I need you to pay attention. Now I want to come here now. Okay, like I said, the lasso is actually going to introduce what I call sparsity into the model. And the function of the sparsity is, of this parameter is to shrink the weaker relationship to zero, so that we can actually say the two variables that do not connect are conditionally independent, or given that we have observed the rest. Okay, which is what I'm trying to say here. If you take a look at this. Okay, which means this guy, which we call precision parameter, one of the entries is what? One of the entries is zero. Initially, one of the entries in the off diagonal, none of that entries is zero. They all connect. Okay, because they all connect, it makes the network to be complicated, and that's actually resolving to interpretation issue. And that was the reason why we are introducing lasso. Okay, now when you introduce lasso will actually sparse your model. It's going to introduce sparsity, and the moment sparsity comes in, conditional independence comes in. The conditional independence is going to say, I'm not going to draw arrow between these two variables. I'm not going to draw arrow because they are independent, given that I've observed the rest. Does that make sense? That's exactly what I mean. Sparsity, Okay, translate into conditional independence. Conditional independence translate into sparsity. Okay, now take a look at this. At the end of the day, if I have so many variables and I've used lasso, the precision matrix is going to look like this. If you take a look at what I'm having now, where you have a star, it means the value there is non-zero. But now we have a lot of zeros in the off diagonal. I just wanted to take a look at that. Having a lot of zeros in the off diagonal, it means, the sparsity parameter is doing a great job. Does that make sense? Because the more you sparse the model, the more the model becomes interpretable. That's exactly what I mean. I think I included an example yesterday on this, the material. I'm still going to update that. Pay attention. Take a look at this. I want to have an example in a brain connectivity. Brain connectivity. Okay. If you look at the way brain work, there's a lot of connections. Okay. Now when you take a look at, if I want to consider activation levels from 4 brain regions, I want to talk about the frontal F, the temporal T, and the parental P, and the occipital O. Okay. And you know what? I can compute a covariance, that explain how this variable co-occur or vary together. Okay. And I'm able to get a precision matrix. Don't forget, if this guy is a covariance matrix, of course, the covariance matrix is going to be 4 by 4 because I got 4 variables. It's going to be symmetric. And of course, and I want to find the precision matrix. Don't forget, the precision matrix is the inverse of the variance or covariance matrix. And let me tell you this, what is the essence of the precision matrix? The precision matrix is the one that tells us the conditional dependency among variables. Conditional dependencies among variable. The covariance structure does not tell us conditional dependency. The covariance only tell us how they vary together. Now, what I'm trying to say the other time is a situation where we got a lot of features that is more than the number of observation. Of course, in that situation, we may not be able to find the inverse of the covariance. Okay, we will not be able to find the inverse. But situation where we're able to find the inverse, okay, what do you see? You actually going to see that in the end, when you find the inverse, there's going to be, in the off diagonal, they're actually going to be, zeros. I mean, not zeros, okay? But when you apply lasso, take a look at what I'm going to have at the end of the day. Now, this is the diagonal. The off diagonal, can you see some zeros? That really makes sense. Okay. Here we have already applied lasso. Okay, the lasso shrink because initially the zeros that you have, there won't be any zero in the off diagonal. Okay, there may not be zeros in the off diagonal. If the moment there's no zero in the off diagonal, then there's a complication. And that's why we need lasso. So the lasso now shrink the weaker relationship to zero. And that was why you have zero in the off diagonal. I'm going to go into another example. Now this time around, I want to talk about stock market dependencies. Okay, stock market dependencies. And I want to talk about 4 assets like AAPL, the Apple, the Microsoft, the ExxonMobil, and JP Morgan. Okay, now, there's possibility somebody could have an asset in all of these. Let me tell you this. When assets relate, okay, if there's a positive relation between 2 assets, it's dangerous. Because if there's a risk in this asset and the risk in the other asset, if they are correlated, of course, it's very, very dangerous. And that, I don't know whether you've heard about diversification of portfolio. Okay, so right now, if you take a look at this guy, this is the covariant that give a covariant structure. how the Apple, the Microsoft, the ExxonMobil, and the JP Morgan actually varies together. And after finding the precision matrix, applying lasso, I'm actually going to have this guy. Okay, I'm actually going to have that guy. Now, what is the meaning of this negative 80? Okay, the negative 80 is you are talking about the the direct dependency. Okay, now the negative 80 now you're talking about between Apple and Microsoft. Apple, Microsoft, okay, they have a direct dependency. Okay, but when you take, oh my God, I needed to take a look at this guy now. That's zero there. Okay, if you take a look at the zero there, then you are trying to say Apple and ExxonMobil, Apple and ExxonMobil are conditionally independent given we have observed the rest. Conditionally independent, we have a zero. You know what I mean? Zero. You know what that zero means? There is no edge between them. Does that make sense? Now we are here, we have already applied lasso. Initially, maybe we do not have zeros in the of diagonal, and applying lasso, we shrink the weaker relationship to zero. And that will induce sparsity. And the moment you have sparsity, you have conditional independence. And the moment you have that, your model become more interpretable. Okay, now I want to go to the model now. We actually relying on the fact that the variables follow normal distribution. And because of that, and that's why I said here, I have x1, x2 up to xn. They follow normal distribution with a mean vector of 0. The variance covariance exists. Now the question now, if I want to optimally obtain the precision matrix, okay, this is to actually do that using the method of maximum likelihood. With the method of maximum likelihood, I'm actually going to set up the distribution, find the likelihood, and take the logarithm of the likelihood. Of course, that is exactly what I'm doing here. But let me tell you this. If I go directly on this, and I got precision matrix, the precision matrix that I'm going to get from here, because when I'm maximizing, I did not include lasso. If I don't include lasso, you know what I'm going to get in the end? The precision matrix that I'm actually going to get in the end will be complicated because I did not introduce any sparsity, the sparsity parameter. I didn't introduce lasso here. Okay, and that was why. Okay, uh so when you take a look at this, is the conventional way, this is a naive way of estimating. What this guy is going to give you at the end of the day is just going to give you the inverse of your sample covariance. You have a sample covariance, find the inverse of that, and that's what this guy is going to give you. But you know what, the of diagonal of the sample covariance will be non-zeros. And if all of them are not zeros, then the structure is complicated. When the structure is complicated, interpretation becomes an issue. Okay, but what are we going to do? I will tell you what we need to do. Now, and that was why, doing this without incorporating lasso, doing this, estimating your precision matrix without incorporating lasso, okay, you're going to have a problem. Okay, but the problem is going to be huge when the no I mean in high dimensional data, when the numbers of features is more than the number of observation, then your covariance will not be invertible. If you're not able to invert, to find the inverse of your covariance matrix, then you are not able to get precision matrix. Don't forget, precision matrix is the inverse of the covariance. Precision matrix tell us conditional dependencies, measure conditional dependencies among variables. And that's what I'm saying here. Look at the challenge that we have. Okay. The classical theory, the MLE only converges to truth as sample size increases, but in a situation where your number of observation is less than the number of features, then there's going to be a serious issue. And that's why we normally want to encourage in statistics, want to make sure the sample size, the number of observation should be more than the numbers of features, but in some situation, it's not going to happen. We normally have in high-dimensional data where the number of features is more than the numbers of observation. Then what are we going to do? Because to obtain a precision matrix in that situation, of course, it's not going to exist. And what we need to do is to introduce lasso. Please pay attention. Oh my God. Who actually introduced lasso is Fredman, Hastings, and Shirani in 2008 in their paper, okay, that they published. They introduced sparsity, okay, and look at that. Look, this is the sparsity, the lasso parameter. The idea behind initially, this is what we have initially from the multivariate normal distribution. That is just the log likelihood of a multivariate normal. Okay, when you get your, a situation where there's a high dimensional data where the number of features is more than the number of observation, you may not be able to obtain precision matrix. And that is the reason why Fredman et al. In 2008 introduced what I call lasso penalty. The essence of the lasso penalty is to shrink, okay, variables with weaker relationship to zero. Okay, and that is a lasso parameter. Okay, it enables the structure to learn. At the same time, it extracts, it separates indirect relationship from the direct relationship. Okay, so take a look at that. Okay, now right now, how do we actually obtain, what I'm trying to show you now? Okay, how do you solve an optimization problem? Okay, where after incorporating the lasso, and of course, in the end, you want to arrive at a precision matrix, that is not complicated. Okay, that's exactly what we're doing here. Okay, that's exactly what we're doing here. Okay, now let me tell you this. Do you know that even with the introduction of this guy, even though it is convex, but we're not able to, at times, depending on the severity of the violation, we are not able to separate the variable independently. I'm going to say that again. We are not able to separate the variable independently. And because of that, we use an approach where we're actually going to extract a column, okay, and we update that column, okay. When we update the column, we put other columns we fix other column, and that's a very approach, that was used is this. Please pay attention, okay. In this approach, it's what we call the blockwise coordinate descent. Okay, in a blockwise coordinate descent, what we want to do is say, okay, if I have several columns, okay, I will focus on one column at a time. When I focus on one column, I'm actually going to fix the other columns, okay, and I'm actually going to perform the optimization. If you take a look at what I have here now, okay, this guy, okay, the precision matrix, we partition that into block, we partition the sample covariance into block, and we partition this guy also into block. Now, what do we mean by this guy? Please pay attention. Okay, this guy is actually all the columns. Okay, you have all columns. Okay, except the one you want to update, except the column you want to update. And of course, this guy, the column that you want to update. Okay, and this is the corresponding partition in the sample covariance as well. Okay, now this very approach is actually fantastic. Like I said, I'm going to please pay attention. This guy is a sub-matrix for all variables except the one you want to update. You know, I said the variables are in columns, right? In your data, right? If I'm focusing on, okay, let me give you this example. I remember the other time I was using a USA arrest data, right? Where we have some violent crime variables and the subpopulation. Okay, now I have assaults and so on like that. If I'm focusing on assaults, okay, if I'm focusing on assaults, I will fix the rest. Okay, that this guy here now is actually the submetrics for all variables except the one that I'm updating. Okay, and this guy is actually the one that I'm updating. Okay, and that is actually going to tell us the precision coefficient that link that variable to the others, which is what we see here. And this is the corresponding partitioning of the sample covariance matrix. But let me tell you this. How does it work? Take a look at this. This is the way the blockwise coordinate descent actually work. Okay, if you take a look at what I have here. Okay, you're actually going to see that you see the W11 and you see theta 12. The one with the 1 1 actually talking about the one that correspond to every other columns except the one you are updating. And the theta 1 2 is the one you are updating. Okay, you continue. So you're actually going to solve here. You're going to apply regression analysis because this is because we have a graphical lasso. We're actually going to use the idea of a lasso regression, and at the end of the day, we're actually going to derive what is our beta. Take a look at this. That is what we derive. That is a beta. You know what that beta means? Beta measure conditional relationship among variables. When beta equal to 0, you know what I mean? When beta equal to 0, it means the two variables are conditionally independent, given that we have observed the rest. Okay, after getting your beta, okay, then we need to do updates. We update. After getting your beta, you update your W, you update your precision matrix. And of course, at the end of the day, like I said, this is what we are optimizing. Okay, I'm actually going to show you the computational algorithm. Let me show you. Take a look at this. I want to explain this to you now, this computational algorithm, even though I'm still going to, give you the hard code, because with the arrow code, it's actually going to be easy to navigate. But what I'm just explaining now is just to explain mathematical aspect of that, what was programmed behind the arrow code, behind the software. If I want to start, I will start with the initialization. What is this? Please pay attention. I'm going to start with that. The W equal to that. What is X? X here is the sample covariance that you get from your data. Now, I want to make sure the sample covariance that I'm using is positive definite. You remember in this class, we talk about positive definite. What actually make this particular algorithm to be stable? And what make the mathematical foundation here to be valid is when the covariance matrix S is positive definite. Positive definite, you remember, we want to make sure in the diagonal, they're all going to be greater than 0. Of course, what occupy the diagonal of a covariance matrix? Can somebody tell me? What occupy the diagonal of the covariance matrix? Can somebody tell me? What is that? Oh, there's a name. When we say covariance matrix, what is the element in the diagonal? What is it called? Eh? Apart from the eigenvalue, there's a name. Variances. And positive definite means variance should be greater than 0. Does that make sense? We want to make sure the element in the diagonal to be greater than 0, and that is why we're adding this. We are adding identity multiplied by lambda. We want to ensure positive definiteness because if the covariance is not positive definiteness, there is a possibility the algorithm of the blockwise coordinate design is actually is going to fail. Okay, now we're going to start with that, and after starting with that, okay, we're actually going to do the partition I talked about the other time. Okay, into 4 parts. Let me go back. The partition into 4 parts here, this guy here, the partition into 4 parts that I talked about the other time. Okay, and after all of that, okay, I'm actually now going to solve. I'm gonna solve this, and after solving that, what am I going to get from that? Of course, I'm going to use a lasso regression to optimize that, and I'm going to get beta, and after getting beta, then I will update. I will use my beta to update the W. And after updating, okay, I'm also going to update the precision parameter. Now, the precision parameter now, I'm using the beta to update that. I'm actually going to get that. Okay, that is the precision parameter. The precision parameter is just like the element in the precision matrix. But let me tell you this. How do I know that this is actually going to guarantee positive definiteness? Because let me tell you this, we're going to be doing update. I told you the other time, we're going to have several columns, and we're going to be doing the update, one at a time. And in every update that we do, we want to make sure the covariance stay positive definiteness. And how are we going to show that? And that exactly, to be able to show that, please pay attention. Pay attention. Masunda and HT 2012. Okay, you know what Masunda and HT 2012 did? Okay, they started with the W that is actually non-negative, and strictly non-negative has to be greater than 0. And you know what they did? They make sure that the absolute difference between the W and the sample covariance is within the regularization parameter. Take a look at this. Less or equal to lambda. Lambda is regularization parameter. So this is how they can actually retain positive definiteness in during the iterative process. Don't forget here, the iterative process, we're going to update this column. After update, putting other column face. After I'm done with this column, I'm going to go to the next column until I'm completely go across all the columns. Okay, and of course we need the covariance matrix to be positive definite, because if it is not positive definite, the algorithm will fail. We don't want algorithm to fail. And that is the reason in some situation where the covariance matrix is not positive definite, the algorithm is going to fail. And that was what triggered the intervention of Masunda and ASTI 2012. And they imposed the regularity condition. And this is the condition. The condition is that if I start with a working covariance matrix or precision matrix, if I start with that, and if the matrix that I start with, I ensure a positive definite, okay, then the only condition under which I can, retain that positive definiteness or throughout is when I restrain, restrict the absolute difference between the working matrix and the sample covariance within the regularization parameter. Okay, and that's exactly what I mean. Now pay attention. When I start with this, to be able to start with that, I actually start with X plus, because initially that very S, that is a sample covariance, may not be positive definite, and I added lambda high. The lambda high is to make sure the diagonals stay positive. Does that make sense? And if it is positive at the beginning, during the iterative process where the updating is going to be taking place, of course, how do we ensure that is going to stay positive? And this is a way to ensure that it's going to stay positive, that was introduced by Masunda and ASTI 2012, where they actually restrict the absolute difference between the W and the sample covariance, okay, to be within the regularization parameter. Now, let me tell you this. What have we done today? And I needed to pay attention. I'm actually going to say this again. Uh, Before I do the recap, you know, the lambda that you see in the sparsity is the one that is actually controlling the sparsity. Okay, because let me tell you this, when lambda equal to 0, then you are not sparsing at all. The model remain complicated. When lambda is increasing, okay, when lambda is increasing, we expect the variables with a weaker relationship to shrink towards 0. Does that make sense? And we need to be able to figure out what is the optimal lambda, okay? And of course, it's going to be done through the optimization process. Now, let me tell you this. The bottom line of what we've done today. We got so many variables, okay? We got so many variables. Oh, before I go into the recap, what is next? We're still going to do this guy with this one more time, where we want to talk about graphical lasso for learning sparse inverse matrices. We're still going to talk about that one more time. But let me talk about having a recap, and I need you to pay attention. Statistical machine learning is like a story, okay? A story that goes on and on and on. Now, let me say this. Whenever I'm considering relationship among variables, and I got a lot of features. So if I have a lot of features, I can actually compute the covariance matrix. The covariance matrix will enable us to measure the relationship between any pairs of variables, how they co-occur or how they vary together. But let me tell you this. If I now want to obtain the conditional dependency, I need to find the precision matrix. And how am I going to get the precision matrix? The precision matrix is the inverse of the covariance matrix. I'm going to say that again. Precision matrix is different from covariance matrix. The covariance matrix is only going to tell you how two variables vary together. It's not going to tell you the conditional dependency. If I want to measure the conditional relationship, then I need to go further by finding the inverse of the covariance matrix. When I find the inverse of a covariance matrix and the inverse exists, okay, in the off diagonal, okay, there's possibility that I'm actually going to have elements in the off diagonal, all of them to be non-zeros. When they are all non-zeros, that model is complicated. That kind of model cannot be, it's not going to be easy to interpret because we are not able to separate indirect relationship from direct relationship. Now, let me now tell you the severe case of that in a high dimensional data where the numbers of features is more than the numbers of observation. Even though you are able to obtain the covariance matrix, you may not be able to get the inverse. The inverse may not exist because the determinant of the covariance matrix is actually going to be equal to 0 in some situation where there's a perfect multicollinearity among variables. What do I now need to do? When my precision matrix is dense, or I'm not able to obtain a precision matrix at all, what am I going to do? What I'm going to do is to incorporate a lasso penalty. Now, incorporating a lasso penalty, okay, the lasso penalty you have incorporated will actually do the job of sparsity. The sparsity is to shrink, any weaker relationship between variable to zero, and the moment it shrink that to zero, then we're actually going to say, shrinking that to zero means you have already eliminated an arrow that connects the two variables, and in that situation, you're actually going to say the two variables are conditionally independent given others. And with that, with the sparsity, of course, your model become more interpretable, not only interpretable in a high-dimensional data where the numbers of features is greater than the number of observation, where practically speaking, you may not be able to estimate the precision, but you incorporating the lasso penalty, you will be able to do that. And that is the bottom line. That is the summary of the whole thing. Before I go today, wait for a very big announcement regarding practical assignment. Make sure you all stay safe and have a lovely day and lovely weekend. Stay warm. But for now, see you on Monday.